Τώρα μπήκα φούρνο.
Okay, so my name is Konstantinos Roptakis, Kostas, okay, from Hellenic Mediterranean University. HMU, our institution, organizes the MED schools. So I would like to thank everybody for all the applicants for the application in our school. So this 30 minutes session is just introduction to the school. We are very happy that we have together Pedro Barquinia from University of Lisbon in Portugal. Pedro is the technical coordinator of the project, of the Emerge project. So he will show you some slides about the Emerge structure, the motivation, the goals. And part of the Emerge, of course, is this kind of webinars and schools that we organize. So Pedro, please, the floor is yours. You can share your screen and do the presentation.
Sure. Let me just share the screen. Okay, you all can see it in presentation mode, right? Kostas, it's visible now?
Yes, it's full screen.
Okay,
yes.
Good. So, good morning, everyone. It's really a pleasure to be here today. Very happy to see a very large number of applicants to this online school. So it's the second school that we do in the project after a very successful first edition in 2023. So I think you will all have a very amazing week ahead with the contributions that were set to this school. And I would like just to get 10 minutes of your time just to explain you what this Emerge project is all about, because it really lives from a collaborative environment. It's really a networking project to foster new collaborations in this field of printed electronics. So let me just show you a bit of context here. So we are a group of partners working in this flexible and printed electronics market, and as you may be aware from the name of this area, we are targeting all sorts of mechanical flexibility aspects, as having very lightweight electronics, very thin electronics, and with a potential lower cost of the production than conventional electronics, and then with many other added features like a lot of customization, biodegradability, easier recyclability. So many aspects are moving this market, as you see here in this recent market study from IBTech X. So there's as you may know, there's many applications for this flexible and printed electronics market, going from retail, healthcare, wearables, consumer electronics, and so on. And it's quite huge and expanding market. So forecasts to $74 billion in 2030. And when we think about systems that we see with the flexible electronic domains, we think about displays like OLED displays, biosensors, and also all the materials that are required to make this. So we also target, as I briefly mentioned, recyclability and the biodegradability and so on. The flexible and printed electronics market is also targeting a very important concern in the world nowadays, which is electronic waste. So you all know that this is a critical problem that needs to be solved. And indeed, the set of materials that we use here can make a big difference on that. So while we are trying to bring electronics to many more applications than what we have nowadays, the way that we are making it is a way that is compatible with the premises established in the Green Deal that we are following now. So about the eMERGE. So eMERGE was a project that started back in 2021, and it's what we call a research infrastructure, and it's pioneering on its own. First, these research infrastructures initiatives are quite interesting, and I will explain you in the next few minutes what exactly does this mean, but also the area where we are targeting about this flexible and printed electronics is very interesting, because it was the first research infrastructure that was done within this area. And so our main goal on these is to make sure that we open world-leading infrastructure composed by the complementary competencies of a group of partners in Europe to essentially open this infrastructure to make user projects. So essentially, a user wants to make a short-term project, 1 to 2 week project, to test some concept or to characterize some devices that they have, and they happen not to have the competences to do that. And you can approach this infrastructure precisely to do that, and in a potentially free of charge way. So there's many partners that can benefit from this. So don't think this is only something that would be useful for an academic partner doing their research. Our target is not only academics, but also industry, SMEs, startups, and so on. And why? Because let's say, grabbing the concept that I was explaining, that I was talking about, if you imagine you have a concept that you want to test, and you want to start driving a business line for that, so you can save time on making that. You can have eMERGE infrastructure essentially supporting you on that. You minimize the risk of introducing new products into the market. And also, as I mentioned, very, very important, you create synergies here. You create a collaborative environment that can give rise to future collaborative projects. So speaking about collaboration, so these are the partners that are essentially composing this research infrastructure. And as you may see here from the map, we are coming pretty much from everywhere in Europe. So Portugal, Spain, Greece, Austria, Germany, Poland. So many countries are providing their expertise on these. And the nice thing on this is that it's really truly complementary expertise. So you have partners here, experts on developing inks to make printed electronics. You have partners with expertise on the printing process. You have partners with expertise on the modeling, simulation activities, on characterization. So all the network complements itself. So it was a long and tough process to reach to this stage where we can offer the infrastructure to the users. So without making much putting much detail on these, just to tell you that. So for instance, we have these networking activities like the school that we are having here, which are essentially targeting the training of a new wave of researchers to make use of printed and flexible electronics. So we are promoting this eMERGE branding to the different partners that can benefit from these, and also a networking activity that's very important, and it will, at the end of the project, be we think a very useful tool for users worldwide, is making these AI-powered knowledge repository that we call KeyBest, that essentially can help you to derive your own processes to within this flexible and printed electronics domain. So essentially, if you are not sure how to start designing your set of experiments to reach a certain goal, we are essentially deriving a tool that can help you to do that. So about the user projects, you can run projects in, like I said, pretty much the entire value chain of flexible and printed electronics, and we split these projects into what we call 4 transnational activities. So you can go all the way from theory, modeling, simulation, design of materials, devices, and systems. Then you go to material synthesis and ink formulation. You can go then to prototype fabrication, and finally, characterization of these prototypes and demonstrators. Okay, so there's complementary tools and expertise to do that. And in parallel, Emerge is also focused on improving the offer that it has to external users. And so for that hand, we develop what we call joint research activities, which are projects or within the Emerge consortium, following these 3 research areas that you see here: hybrid printing setups, high throughput novel inks or pasted synthesis, and then functional 3D printing. And so we try to make these projects in a way that we have outcomes coming from these projects that can then go to these transnational access activities. So users can benefit from increased expertise from the Emerge consortium in that. So finally, the question is, how can you benefit from these? So besides these initiatives that we are putting here today with this Emerge online school, you can actually submit your own projects to implement in any Emerge partners. And so the way that it follows is pretty much straightforward. So you just log into our website, and in the website there will be a detailed description of all the criteria for eligibility. How do you need to make your proposal? But in a nutshell, it's essentially a 1 to 2 page proposal maximum, okay, where you are describing you know, what's the scientific case, what's the experimental plan that you want to follow, and so on. And once you establish that, there's what we call a technical license that essentially is going to check about the project feasibility, and if it's viable to make technically within the consortium, then we move to external reviewing process, just like you have in a scientific paper, for instance. And so these experts analyze the scientific context of the project, and if it's approved, then you can work again with the technical liaison office in a suitable work plan to set up you know, the dates where the project will be executed, if there is some adjustments that need to be done, if you need to send previously some material to make some preliminary tests, and so on. So in a way that the access is turned easy for you. And you can submit these projects every time, so it's always open, the website to submit your proposals, and then each month we grab the proposals that were submitted during that month, and we send these to evaluation. Okay, and so what you can benefit is, like I mentioned, the free of charge access to Emerge facilities. So free of charge in the sense that we are covering travel and accommodation costs within certain limits, of course, and also the costs of accessing the infrastructure. So you can use the set of equipment and the expertise of the consortium for free. And then at the end, you just need to provide a small user feedback and a short experimental report of the experience. So some statistics so far, just to conclude. So far we had 111 projects submitted, and 75 projects out of these were accepted. And so we are helping 149 users for now to implement their projects. And as you can see here, we are supporting a lot of different nationalities, 37 nationalities so far, both within Europe and outside Europe. And a very nice indicator also is that not only academic users are benefiting from these, but also SME startups and the industry, which take something like 33% of the total users that already benefited from the merge infrastructure. And so finally, we are in our 9th call for proposals that is open. So with a cutoff date at the end of April for evaluation. So if you are interested on these, and I'm pretty sure that after the presentations during this week, there will be more and more interest in this flexible and printed electronics and optoelectronics domains. Feel free to contact us to understand if there are any doubts, to submit your proposal and submit these proposals to benefit from eMERGE. So with this, I would really like to thank you for your attention, and I wish you really a very fruitful journey during this week in this online school. Thank you so much.
Thank you, Pedro, for this very nice presentation and the overview of the eMERGE project. So we have some minutes more till the first webinar. Let me share my screen, give some slides. So can you see the full screen? Because I have full screen. Okay.
Yeah, we can see it.
Okay. So my name is Kostas Dragoudakis. I am also the interface office of the eMERGE, the interface office leader. So this interface office is between the users, the applicants of the infrastructure and the consortium members, the host institutions. Let me focus now to the second school. This year topic is the responsible electronics. When we say responsible electronics, of course, we mean sustainable devices, eco-friendly, let's say, and we cover all the value chain from materials, inks, manufacturing processes to be also sustainable, up to device demonstrations and applications in real products. So this is what we try to do also in this school, to cover all the value chain from materials up to devices and applications. And some highlights are presented in the poster that we share. This is the panel, the webinar speakers. We are very happy that we have with us this kind of excellent, distinguished professors, researchers from universities, even from companies that will deliver this webinars in the school. Just to make focus a little bit about the distribution of the topics of the seminars. So we split them in different, let's say, sessions or topics. One part is related to the materials for energy and electronics and chips. For example, we start the school today with Professor Andrea Ferrari. He will speak about 2D materials and their applications in the real products. Of course, applications from covering a wide range of applications, sectors from energy to electronics. Also, today, Professor Mario Lanza will speak about hybrid 2D CMOS electronics. So using 2D materials together with conventional CMOS electronics towards hybrid chips and real microelectronic devices. And another example is the talk of Professor Aldo Di Carlo. He will speak about sustainable solar modules using 2D materials, graphene and other 2D materials. The second, let's say, category is emerging multifunctional materials. Also today, Professor J.Milic will speak about layered hybrid perovskites, 2D perovskites, and their applications in emerging devices. And tomorrow, Professor Guerrero will speak about transient measurements in halide perovskite memories of devices. So we cover neuromorphics, let's say, using perovskites. The third family is sustainable materials. This is the main, I think, the core of the responsible electronics, let's say, activities. That is very important for EU nowadays. So we have a series of webinars. We cover materials based on natural resources for printed electronics, sustainable inks, and specifically for screen printing manufacturing towards sensors and actuators, robotic applications. Also, we have Dr. Hau from FCJ that will speak about robotic systems to speed up the prediction, the discovery of novel materials, and how we can use this automation for high throughput fabrication of devices, covering from solar cells up to other applications. And we have also a very nice talk for LCA. So life cycle assessment is a very important, let's say, activity, because we have to predict, we have to estimate the environmental impact of this kind of devices. So this is a very important activity. Another pillar is sustainable manufacturing. Of course, you have to develop the, let's say, green type of materials, but then you have to fabricate devices in a more, let's say, greener approach compared to conventional silicon microelectronics. So we have a series of webinars for screen printing and inkjet printing on sustainable electronic substrates. Here you will hear about printing devices on paper or even on wood. That is, of course, green material. And also another webinar about high-resolution printing technologies, because we have to scale down the features of the devices if you want to increase the performance. And webinar for printed electronics, printed electrodes. And again, okay, a small overlap, how we can assess the environmental impact of this kind of manufacturing technologies. The last session is the device applications. Again, the webinars address many topics. One is about, this is from a company, BitBrain, about healthcare applications and about wearable patches and wearable devices to monitor some diseases and some, say, medical applications using printed electronics. Another speak about transient electronics, sustainability from cradle to grave. Another example of neuromorphics given by Elisa Donati, and another application on energy, and specifically on tandem photovoltaics on flexible substrates. So we have also two different talks highlighted in black here. One is about geopolitics using emerging microelectronics. This is related to the EU resilience on, regarding IPs and technology IPs compared to other, let's say, parts of the world. And we are also happy that we have together Dr. Isabelle Obieta, that she's an officer, EU officer, and specifically she's the officer of the Responsible Electronics Code that recently announced from EU. So I think she's the best person to give us an overview on how important it is for EU and other countries, of course, and other parts of the world to develop responsible electronics, and of course target real products using this kind of greener technologies. So just to finish this introduction about the school, as we also, Irini Kosoroubi, she's the project manager of HMU. She's responsible for the communication between you and Emerge. So at the end of after the webinars, you will enter this Moodle platform, and then you will have to to answer to 100 multiple choice questions based, of course, on the webinars. And the top 25 candidates will be, let's say, eligible to participate to the second part of the school. So the school is a hybrid school. One part is the webinars, and the other part will be on-site training in Portugal for the top 25 students, applicants. In Portugal, you will attend some lab experiments, and also you will split in different working groups, targeting a different small project. And at the end, you will have to summarize the activities of each group and give a presentation. And at the end, the applicants that will follow, of course, the webinars plus the on-site training part. So they will have all this hybrid school. They can receive these free ECTS credits through their universities. So this is the introduction part. Many asking about the certificates. Like last year, we can give certificates of attendance for the webinars. We can record your attendance in the webinars. We will place a threshold about 30%. At least 30% of the webinars you should be able to attend, and then you can give a general certificate of attendance. And of course, the students, the applicants that they will also attend the on-site training, at the end they will have an official certificate for the whole school. So with this, let me stop sharing my screen. I think we are on time. We are very happy that we have together Professor Ferrari from the University of Cambridge. Nice. So let me tell you a few words about Professor Andrea Ferrari. So I think everybody knows him. We are very happy that he will give the first webinar. He will speak about the roadmap to applications of graphene and related materials. He was a key person of the graphene flagship the last 10 years in Europe on developing 2D materials and, of course, demonstrating applications or products using 2D materials. Professor Andrea Ferrari received his PhD in electrical engineering from the University of Cambridge after a degree in nuclear engineering from Polytechnical School of Milano in Italy. He is a professor of nanotechnology and fellow of Pembroke College. He founded and directs the Cambridge Graphene Center and the EPS RC Center for Doctoral Training in Graphene Technology. He chairs the management panel, and he is the Science and Technology Officer of the European Graphene Flagship. He is a fellow of many societies. So he is a fellow of American Physical Society, the Materials Research Society, the Institute of Physics, the Optical Society, and he has received numerous awards, such as the Royal Society Brian Mercer Award for Innovation, the Royal Society Wolfson Research Merit Award, the Marie Curie Excellence Award, and the Philip Leverhulme Prize, the EU 40 Materials Prize, and many others. He has received also 4 European Research Council grants. So with this, I would like to give the floor to Professor Andrea Ferrari. I think you can share your screen directly.
Yeah, thanks for the introduction. Let me try to share the screen and see if the presentation works first. Okay.
Yes.
Okay. So do you see in presentation mode yet, or?
Not full screen. Now we see the split screen.
Okay.
We have to share the other screen.
What about now?
Now full screen. There is a shadow.
What about this?
Yeah, we can see the full screen, but there is a shadow, a gray label.
Okay, let me try again in a different way. Can you see it now?
Yes, now it's clear.
Okay. Okay, so you can see it full screen now. Hello?
Yes.
Okay, so sorry for the slight delay, so I can now start the presentation. And okay, I can now see the video panel as well. That's fine. So I'm going to give you an introduction on graphene and related materials and looking at the timeline from the beginning until nowadays, or what the applications are. But I prefer to really start from a different topics, because when we consider new technologies, we need to see what happened in similar technologies before. So we are all familiar with electronics, and when was the first transistor devised? This was the first transistor in 1947. And you can see it is at the Bell Labs, Shockley, Bardeen, and Brattain working on it. And whenever I look at this picture of the first transistor, the first thing that comes to my mind is sort of Fred Flintstone working with stones and doing his day job. So truly, this is a very surprising device, if you consider what happens nowadays, where all the transistors are everywhere. So if you put yourself in 1947 and you say, okay, I go to a big electronics company with this bunch of rocks, and I tell them, okay, by 2024, you're going to have a fantastic mobile phone with thousands of these or millions of these transistors doing all sorts of functions. Of course, nobody will believe you. But this is exactly what happened at the time. A lot of effort was put into this. And it took until 1958 to have the first integrated circuit. So we are talking about 10 years development. But if you look at this picture and you consider 2024, you would agree with me that if we take a very sort of bad lab almost everywhere in the world, and an average to bad student or postdoc going there, they would be able to create this device very, very easily. And yet that was 10 years of development between the 40s and 50s. And also, more importantly, the first sort of modern-looking device, like the MOSFET, came in the 1960s. But the other thing that happened in the meantime is that for the first several years, the work was done on germanium, because that's what was the material used at the beginning. And only almost after 10 years, they decided that silicon was better due to a variety of reasons, in particular, the very good native oxide. So it's like saying, we mentioned before the graphene flagship, you work for 10 years on graphene and then say, oh, I'm sorry, all what we have done is sort of useless. We now have to start from zero on a completely different material. But that's exactly what has happened, and historically. And so this is typically what happens when you develop a hardware-based technology. And if we go many years ago, 10 years ago, 2014, this is the 14 nanometer node of the 3-gate transistor. So how much money does a single company invest to develop one node of a technology? And that's about $10 billion. So that's the investment needed in order to develop each of the new nodes by one individual company. So again, if you look at the Graphene flagship, was about 500 million net investment over 10 years in 160 institutions. So it pales when compared to what individual companies are doing now nowadays. In fact, you know the situation now. This is already very old. If we look at the 2 nanometer nodes or 3 nanometer nodes, there are only essentially 2 places in the world where they can be made: TSMC in Taiwan and Samsung, but Samsung is a private company. And for this reason, the US and also Europe have launched the respective CHIPS Act, and US is doing a massive investment to try and bring this technology back there. If you think about an extremely small gate channel technology nowadays, and you want to build a factory, it will set you off $25 to $30 billion to do this, plus many, many years in expertise that is not needed. So it takes, and this is 2024. So we have been working on the concept of the transistor since 1947. So it's not special or surprising that it takes many years to go from the initial concept to the more refined development of a technology, and it requires a lot of investment. So when are we in the case of graphene? So we have this sort of hype cycle, and as the technology trigger, the peak of expected inflection, probably this was around the time of the Nobel Prize. So at the moment, in my view, we are here. We are sort of on the slope of enlightenment, where it's becoming more and more clear what options and applications exist for graphene, and what is useful or not. And we are getting towards a time where there are going to be applications. So again, let's look at what has happened in a relatively short period of time, because I remind you that this is actually a real picture from really 2004. That is a real piece of graphene of 2004 taken by AFM. So that was graphene in 2004, a piece of a flake of only a few microns in dimensions. But already by 2010, thanks to the effort of Samsung, and previously in 2009 of Texas Instruments and SKKU in Korea, 30-inch production of graphene was achieved. And 2010 is also the year of the Nobel Prize, and this picture was in the extended motivation of the committee, and it's clear why they were also convinced. But it took only 6 years to go from 1 micron to very large area. Within the graphene flagship, and also in the UK, in Cambridge, there is a company called Einstein. In fact, this company was the spin-out of our department called Nano Instruments, and then in 2006, it was acquired by Einstein, Germany, but the company stayed in Cambridge. And they started producing systems for the large-scale growth of graphene. So first is 4 to 6 inch systems called BM Pro, and then they developed bigger system, the BM303, which is a 300 millimeter wafer system, and the Newton system, which is a continuous roll-to-roll system for the production of graphene. So let me skip one slide, but just to give you an example, with a single BM303, you can produce 1 to 2,000 square meters a year of graphene on wafer, on silicon wafers. While with a Newton system in a roll-to-roll production, you can produce between 10 to 20,000 square meters of graphene a year. That's only with one individual system. And what is happening is also the price per square meter is massively decreasing, and we are going quickly towards the sub 10 euro per square meter price for the production of graphene. Now I will skip a movie, but I will show you the latest system. This is called the close-coupled showerhead MOCVD system, CCS2D. So we just installed one also in our department. And this system is the evolution of the previous ones and allows to go up to 300 millimeters. We have an 8-inch system because we don't need 300. Not just graphene, but also HBN and many of the other layered materials, and you can also grow heterostructures on it. But there is another way of producing graphene-related materials, which is the liquid phase exfoliation, relevant, of course, for printed electronics. So in 2008, Johnny Coleman at Trinity College Dublin approached us to discuss about this possibility. And the reason was that for many years, people were debundling carbon nanotubes. So in carbon nanotubes, the issue was that all the nanotubes, when you were making them, they were sticking together and you wanted to individualize them. So there were different approaches to remove one nanotube from the other, and those were based on some sort of solvent that went in the middle. So the idea was kind of very simple. At the end of the day, the wall of a nanotube and a graphene is basically the same stuff. So can we take graphite and chuck it into some solvent, sonicate, and then ideally get 100% monolayer graphene flakes? So that was the idea at the time. And it was Jenny Hernandez, the student at the time, now she's a professor, that did this work and was published in 2008. And quite interesting, the title of the publication is High Yield Production of Graphene by Liquid Phase Exfoliation. But if you read carefully the abstract, the yield was not 100%, but was 0.8%. Well, it still claimed that to be a high yield because before the yield was 0. So 0.8 is much bigger than 0, especially if you do the ratio. So it took about 10 years to develop a system which we call the high pressure homogenizer, and you can see it here, and to produce graphene in large scale. So you basically throw this graphite system in a graphite flakes in a system that has some diamond channels with some very steep turns, and these create a large shear force that extracts the individual flakes of graphene. And you keep repeating this many, many times, and you end up with around 100% yield, which means 100% or close to 100% of the graphite that you put in is actually exfoliated. And again, the whole trick of the process is in the design of these channels with a very sharp turns, and the microfluidics is being still now investigated into the details to know exactly what is going on. So once we had the inks with graphene already in 2008 and 9, the first thing to do was to try and print. And that's what was done. I don't know, Konstantinos, can you also hear a sound of the printer or just the picture? Only the picture. Sorry? Sorry, did you hear the sound or as well? Yeah. Yeah, okay. So there's a quite noisy sound of the printer. And basically, this was used to print something not very useful, the University of Cambridge logo, but it was the beginning of the use of these printed graphene inks for a variety of applications. And of course, at this school, there will be many, many, many talks on the topics, but just to give you an example, people have used printing of graphene-related materials for optoelectronic devices, for antennas, for batteries, for sensors, for PCBs, and for smart textiles. So I will only give you some representative examples here. One is this one. This is very interesting because it's one of the first interactive posters that we did. So we gave the bottle of graphene to one of our of the shops close to Cambridge. They print, these guys, they literally print posters for conferences and so on. And just by doing screen printing, we had the device printed. And so you can see this is another example done with a company called Novalia, that is another startup, a spin out of the university. And these are the sensors and the printed PCB. And then after that, we were able, you can put a color on the top of this, and you get these printed posters that are interactive. as you can hopefully see here. So the sound is not great, but basically you can play these posters, get music out of it, and everything is made with paper. So with time, of course, not only 2D printing, but also 3D printing became interesting. So we were able to do extrusion of filaments and then 3D printing of filaments. And within the graphene flagship, these composites that were then developed, for example, by Avanzare, that they have set up a very large new factory now in Spain, or in Cambridge by Cambridge Graphene, a company that we founded and was then taken up by Versarian. And you can see the capacity already many years ago when they started, it was 0. And already by 2019, it was several tons per year. And that's the facility where they started doing the production. And these inks were used in, for example, sports equipment. This is skeleton that was used for the Olympic Games. These are headsets. And also there are collaboration with industry for using these materials for different ways. One of our postdocs, Francesco Bonacorso, then went to Italy and started another company called Bidimensional. And again, based on graphene ink, he presented already many years ago this helmet that uses graphene composites starting from a graphene ink. In Manchester, in collaboration with Aidale, they started testing this for aerospace application. So these are composites that are produced starting from the inks, and this is a drone where the initial testing is done. Within the graphene flagship, we had a long-standing collaboration with Airbus, and this is the leading edge. You can see the edge of the tail of a Boeing, of a Airbus A350. And this was done and tested in collaboration with the National Research Center, CNR in Italy. And this has been used for de-icing and other applications. Something else that is quite interesting when it comes to graphene are applications in space. This is a collaboration that is being on within the graphene flagship for many years, involving the CNR in Italy, the Leonardo, which is the biggest aerospace company in Italy, and the European Space Agency, led by the University of Brussels, where the space know-how lies within the graphene flagship. So one of the problems that satellites face in space is that even though space you think is very cold, in reality there is a phase of it that is exposed to the sun, and it becomes very hot. Plus, of course, internally, you have all the electronics and everything else that creates the heat. So there is a need to remove the heat generated internally and externally to the heat sink. The heat sink is clearly the outer space. So in order to do this, you need a pump. If you have a normal pump with moving parts, this can be broken. As you know, and you're familiar probably when you look at air conditioning systems or plumbing systems at home, they keep getting broken. So it's very inefficient to go to space and repair this. So the idea is to use capillary pressure. So to use this metal wick with some pores. And when this is heated up by the internal or external heat sources, it evaporates a fluid that is circulating within the satellite, removing the heat, and then there is a condensation, evaporation, condensation, evaporation. So this system does not have moving parts, so the only part that moves is the fluid, and also doesn't have a switch, which is a problem, because if you don't have a switch, you have an issue, because if it doesn't start, you have no way of intervening. So it has to be very well set when it comes to self-starting. So why using graphene in this case? So you take this metal wick and you put graphene on it. So you increase the wettability, so you reduce the startup time. The layering of graphene creates a preferred liquid stream. You increase the wet thermal conductivity, so you help transfer graphene from the source located outside the seal shell to the capillary inner bore of the pump. And also another effect, that graphene is reducing a little bit the size of the pores because it coats them, and this increases the capillary pressure. So this is the first system that was tested. And so it was in a box with, you have the condenser, the evaporator, and everything else. And the measurements were done in zero gravity flight. Zero gravity flights are provided by the European Space Agency. You can see me not doing the tests, but trying to float in zero G is not easy. If you've never done it before, floating in air is not the same as going in water. So besides me enjoying myself, so this was actually a very successful experiment with performance much better than what was presented before. The next step was to test it with an extended flight in space. And there are some rockets that you can use. They are called the sounding rockets, and they are sent by the Swedish Space Agency in ES range, which is the European Space Agency range. And this sits 200 miles north of the Arctic Circle. So in the winter, there is always snow and dark, and in the summer is very nice. And this was an experiment of a few years ago. And the one in the center is advanced research on liquid evaporation in space. Basically, the idea was, can we do printing in space? And why do you want to do printing in space? Because in a long-term space flight, you would not bring some spare parts, but you could bring, for example, bottles of inks, and those can be used to print new components. So this is a few pictures of us in the summer in the launching range. And as I said, we also did it in the winter. And for example, it's nice because in the winter you can see very nicely the Northern Lights, and that is the Maser 15 that we launched. And this is the launch of the satellite of the experiment that was done last year.
-10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
And after a few seconds, you have the sonic boom and so on. So this is then splits in two stages and allows you to do the experiments for a few minutes in space. And this, on the other end, is the launch in the summer. And this was 3 in the morning, but there is always light in the summer there. And then after a while, the second stage, as you saw in the picture in the winter, detaches, and you will see it happening in a few seconds here. And then after the detachment, you can see it's gone. And there are some weights that are launched so that everything is stable. And then during this stable time, you can do your experiments. And then the rocket comes down and you go and collect it and do the work. So the next step was to go to the moon. And in collaboration with Khalifa University and the Emirates Space Agency, as well as Fraunhofer, MIT, and many others, we have produced a set of experiments to go on the wheels of this rover, or this lunar rover, to study the interaction with the dust on the moon. The dust on the moon is called regolith, and this is a very nasty material that is very sharp, and of course it is sharp because there's no atmosphere. So unlike what you may think, this lunar dust can actually cut into equipment, into the joints of the spacesuit, and it will be one of the biggest issues to establish a colony on the moon that is going to happen now. So we had a task to do this work, and then in December, there was a launch. This time to go to the moon, we used SpaceX, so from Cape Canaveral, and this was sent up in this rocket, and you can see the launch of the rocket here. Of course, a much bigger rocket than the one we saw before, but at the end of the day, once we see one rocket, they're all sort of more or less the same. And then after a few months, because this was a low energy mission, instead of using a lot of fuel to go there in 3 days, it went up to 1.5 million kilometers and then was attracted back by the gravitation until on the 25th of April 2023, we were ready for the landing. And you could see these pictures. These are pictures seen by the lander while it was approaching the moon. And this dark spot is the shadow of the moon on the Earth. And then it was approaching the moon, but then in the final seconds, people were a bit worried. And as it turned out, the lander crashed on the lunar surface because of the miscalculation in altitude. There was a problem with one of the sensors, and eventually the lander and the experiments destroyed on the surface of the moon. However, because graphene is so stable and there is no atmosphere, I'm sure the graphene samples are still there. And whenever somebody in the future will do some archaeology and visit the site, this will be the first graphene that at least crash landed on the moon. And now we are planning for new experiments. You've seen that many other countries and also private companies are now aiming for the moon because of the colonization, or I mean the settlements that are going to be there. Now, graphene is only one layered materials, but there are many others. And you know, HBN is, for example, an insulator. MOS2 is a semiconductor. Niobium selenide is a superconductor. So how many of these materials do exist? There was a very nice work done by the group of Nicola Marzari within the graphene flagship, where they used density functional theory and other theoretical approach to look at all the databases of known materials. And long story short, they determined that at least 1,800 materials exist in nature that can be exfoliated. Bear in mind, many works have been published since then, and this estimate varies from 1,800 to 5,000. So we don't know exactly how many, but there are many, there are thousands of them. And then there are other materials like the MAXine that they don't start from layered materials when, because they have covalent bonds in the max phase. So this is, and that's another 80 or 90 on the top of this one. So the graphene is just the tip of the iceberg when it comes to the number of materials that can be exfoliated. And of course, the research has progressed in these years, first with the individual materials that have to be exfoliated. And this you can consider like the ingredients of a sandwich, the lettuce, the cheese, the meat, and the bread. And then what is more interesting is when you put these things together to create an hamburger or a sandwich. So if you buy one of these things and you eat it, is not the same as getting an individual piece of salad or cheddar and so on and put it in your mouth. And the same happens here. When you take the individual exfoliated materials and you stick them together, if you have clean interfaces, you really can create completely new properties that will not be the linear combination of the two ingredients that you are considering. So now there is a lot of effort going on to create these heterostructures at bigger and bigger size all the time. And so we have all this class of crystalline materials, so graphene, boron nitride, but also you can functionalize them. For example, the fluorographene or the graphane, which is graphene functionalized with hydrogen, which we did in 2009 with Manchester for the first time. Then you have WS2, MOS2, and so on. And then you can stick them together to create new materials that don't exist in nature. They are completely made artificially or by hand. And not only the arrangement of the layer, one with respect to the other, gives the properties, but also the relative orientation. For example, let's take graphene, 2 layers of graphene, one next to each other. If you change the angle, you can go from a metal to a semiconductor, to an insulator, to a superconductor. And in fact, at the magic angle, in 2008 and 2009, the group of Pablo Jarillo at MIT has shown the superconductivity properties and related to the presence of flat bands. And this is really has initiated or spurred a large field of research. Something else that happens, you can have the so-called moire materials or moire properties. So when you have the interaction of the two, layers, you can change the optical properties for emission, absorption, and many of other things. And as I mentioned before, this system of Einstein can produce samples of different sizes, but also of different materials. This is an example of a wafer scale WSE2 up to 8 inch and grown with this system. But not only CVD on MOCVD, and already in 2011, it was possible to do the exfoliation of any of these layered compounds, so boron nitride, metal calcogenides, and so on. And this is the work of Johnny Coleman in 2011, showing a variety of bottles with different compounds, with different solutions. And this can be extended as much as you want. So these are different 2D material-based inks, HBN, MOS2, graphene, and so on. And this is the log of the Cambridge Graphene Center, which was printed using these different materials. So we have this platform of printable materials that can be used in web coating, spray coating, injetting, flexo, screen, gravure, offset. So all of these techniques have been used over the years. As I said, this field is now almost 10, 15 years old. And all sorts of things have been printed, photovoltaic system, batteries, supercapacitors, antennas of different types, stretchable and flexible electronic systems, as well as different kind of displays. So now let me take this field of exfoliation and graphene in the area of optoelectronics, and I will show one example because I think the time is over soon in optoelectronics. So the real reason, or the reason why graphene got the Nobel Prize, or the Nobel Prize was awarded to graphene, sorry, is not because of the Scotch tape experiments or the exfoliation, but is because of this experimental verification of the Dirac cone, where you have this massless Dirac fermions. So the electrons behave as if they have no mass, and they obey the Dirac equation. So this is the deep physics that was at the beginning of graphene. But also, if you look at the Dirac cone, immediately it tells you that the material is ideal for optoelectronics, because if you arrive with a laser of a certain wavelength, you can always excite an electron-hole pair, no matter what wavelength you're using. And that's quite unique. No other, if you take a material, they usually have a band gap, or even a dot with subbands, you will only be in resonance with one or of the subbands for a given wavelength. Here is like having an infinite number of subbands. So what happens after the optical excitation? So there is you create a out of equilibrium population of electrons, and this relaxes towards the ground state. I wrote here 100, but in reality, we know it's more like 20 to 30 femtoseconds. And you can also then have cooling by phonon emission, but that happens on a picosecond time scale. And actually, quite interestingly, but I will not discuss, they can also recombine and emit PL. This is ultra-fast PL. And by the way, because of the interaction of electrons, the PL can exit, and energy of the PL can be higher than the incoming optical pump, which is quite weird because usually it's lower, but some electrons can be excited to higher energy and then recombine. However, let's forget about this and let's consider how to build a laser. So in order to build an ultra-fast laser, you have to essentially use two mirrors, one non-transparent and the other one semi-transparent, otherwise the light doesn't come out. And then you need to put your gain medium in it. And then you need to put what is called a Saturn absorber. So a Saturn absorber, like as I showed before, is a material that absorbs light. When the light is absorbed, it lets light through, and then the light gets absorbed again. It's like a sponge that you put under the water, and until the sponge is full of water, it will absorb water. And once the sponge is full of water, the water gets through, and then you have to squeeze it in order for the sponge to work again. The good thing with graphene and with other what are called passive Saturn absorber, the squeezing process that you do with the sponge is happening automatically due to the relaxation. And that's what you do in order to bring a continuous wave laser to become an ultra-fast laser. And how do you do this graphene? You can do, for example, by liquid phase exfoliation and printing, as I showed before, or by chemical vapor deposition. So let's consider liquid phase exfoliation. You create a graphene dispersion, then you use some polymer and you create a composite. Bear in mind, this composite is built for optical properties, is not a mechanical composite. You don't need a big grafting. You don't need the oxidation or the anchoring side for the graphene. Graphene has only to sit there in order to be then inserted in an optical fiber. So that's the top of the optical fiber. You see a small piece of graphene put there and then put it into a collector. Another option to do this, you take your optical fiber and you can, instead of interacting directly at the top, you can interact at the side via this evanescent wave. So you cut the fiber in a D shape to have the evanescent field interaction, and you spray coat, for example, graphene on the top of this, and then graphene will interact with the light along the length of the fiber by evanescent field interaction. And what is more interesting here is that this could also be done by CVD, of course, is that you can take multiple cores, each one with a different wavelength, and you can put a piece of graphene on the top, and this will work with all of them at the same time because of the broadband nature of graphene. So as I said, you have the dispersion, we have the integration. Another option is to do vacuum filtration and put the graphene on the top of the quartz, and that you can put this in the system. For example, at the top of the mirror, in one of the mirrors that we have in the system. So the applications, of course, in fiber lasers. So you can take this graphene Saturab absorber, you stick it into a cavity. So you have an erbium dope fiber, which is your gain medium. Then you have a multiplexing system. You have the pump laser diode, and you have a tunable filter and isolator and so on. And then you have a very simple and compact design that is alignment free and is environmentally stable. And this can open up a lot of possible applications and we are going to look at one of them today. So this is the first mode lock laser made with graphene many years ago, 2009. It was then packaged, and you can see in the screen these pulses, and the pulses are the pulses of the laser, which were detected by using a photodetector. But more interestingly is this movie. This is the tuning of the wavelength. You can see that the laser is working continuously across over 30 nanometers, because again, graphene doesn't care what the wavelength is. Who cares about the wavelength is the gain medium, so the limitation here was the gain medium itself, not the graphene. So we have these fiber lasers that can operate in a broadband, and as I said before, the limitation was the gain medium. So how to make it larger is to change the doping of the gain medium. So if you want to work in the infrared, you use terbium doping. In the near infrared is erbium. In the 2 micron region is thulium. In the mid infrared is holmium, and so on. And all of this has been done over the years. So people have been, ourselves, we published tens of papers and so on. And then you have other tricks in order to broaden the emission. But let's now park for a moment the concept of the laser aside and introduce a new concept, and then see how the things can come together. So we are all familiar with Raman spectroscopy, which is a very useful technique to, for example, characterize graphene. But the fact is that it's not so quick if you think about large-scale mapping. If you take a piece of graphene and you want to take a decent Raman spectrum, it will take you, I don't know, 30 seconds and so on. This is far too long to do applications that require mapping. So in biological systems, optical spectroscopy is very much the standard, because you can look at cells and tissue on a submicrometer scales. It provides a much higher spatial resolution when you compare it to magnetic resonance imaging. And then there is fluorescence microscopy, where you use dyes or different markers to have very high sensitivity down to the single molecule limit. So this is all nice. However, there is an issue. So all these fluorescent markers that you put cannot be implemented with certain cells or tissues. So because it gives a perturbation to the system. In any case, think about it. You are studying a molecule, and then you put this marker on the top, and clearly, and if you want to study the kinetics, the molecules will be slower, so it's not going to be good. So as I said, in small molecules, the dimension of the marker is comparable or bigger than the molecule itself, so interferes with the biological functions. And in many clinical applications, staining is not possible. Certainly, you will not do it during a surgery. So there is a need for an intrinsic label-free imaging methods that don't require the introduction of fluorescence. So if we compare spontaneous, which is the normal Raman that we have with spectroscopy with coherent Raman, so what is the difference? In spontaneous Raman, we have one laser that goes on the sample, and there are vibrations that are thermally excited, but they are all incoherent with each other. And so we then scatter with them and get the signal. In coherent Raman, actually, we use two lasers. One is the so-called pump, and the other one is the Stokes. And the difference in energy between the two lasers is tuned to be exactly the vibration of the molecule that you want to study. So, and if you do so, then you have all the molecules are pumped coherently and probed coherently, and the difference between the two lasers is the vibration that you want to study. And what this gives you is an enhancement of 10 to the 5 or 10 to the 10 times of the signal, which means that something that could take a minute could take, you know, a microsecond or a few microseconds to measure. So there are two types of coherent Raman. One is the stimulated Raman scattering. So this is the process. You have the pump and the Stokes, and the output is a gain on the Stokes and the loss on the pump plus the anti-Stokes. And so this is the stimulated Raman gain and stimulated Raman loss, and you can measure this in order to get your peak intensity. Or the other one is the coherent anti-Stokes Raman scattering, when you have two pump signals, and then you are ending up with with an anti-Stokes signal that is the frequency of the phonon. So it's either an intensity change or a frequency change. I'm not going to the details of how this works, and it's realized it's not important for today, but an important point is this. We have only looked at the single vibration, but of course, if I want a Raman spectrum, so I need all the vibrations at the same time. So I need to have at least one of the two lasers, the Stokes or the pump, to be tunable. And that tunability allows us to look at all the vibrations at the same time. So going back to the biology, how is tumor diagnosis typically done nowadays? So you do a biopsy, and then there is some stain that is called a dye that is put on the top of it. And this colors your biopsy with different colors. And then the doctor looks at them, and the brain of the doctor, they're not using equations or anything like that. They look at it like when you have an art critic looking at a painting, and they basically say, that's the healthy, that's the tumor, that's the boundary, and so on and so forth. So it's a human process, not objective, and then there are many false negatives and so on. So it's based on the opinion of your histopathologist, and that's why people have to take a second opinion and a third opinion when people are sick. And there are many false negatives and so on. So the solution, what is the solution? Spontaneous Raman has been done for many, many, many years for tumor identification, as you can see here. We do good specificity and good sensitivity. However, as I mentioned before, the problem is it's too slow to be applied properly. So the goal is, can we build a fast and broadband coherent Raman microscopy system that has a broadband, high-speed properties and allows real-time classification of cells and tissues? So you will get an image, but this will not be a picture. This will be a Raman map, and each pixel would have a corresponding Raman spectrum. So that's what was done. Let me skip a few slides. So this problem has been known for years and people have solved it. For example, Leica is selling a system that costs about 1 million or 1.5 million euros that is based on these tunable lasers. As I mentioned before, you need a very broadband tunable laser, otherwise you don't get the spectrum. And once you put everything... Sorry?
We have still 5 minutes.
Yeah. When we look at these systems, they have the OPO, the pump, and everything else. So it's very difficult and complicated system to use, and it requires a postdoc. It sits on the optical table. It's very expensive. So is there another way around this? And that's where everything comes together. So what if, as I mentioned before, we create graphene ink, and then we put this ink inside a polymer, and then we use this ink as, this ink to create a Saturov absorber that we put it in the common leg of 2 different lasers. So one laser works at 1 micron, and another laser works at 1.5 micron. As I said before, graphene works at any wavelength, so if you put it in the middle, it would mod lock both of them. So this would be not very surprising, and that was the original idea of the experiment. So if we look at the oscilloscope, the laser starts, there is a few fluctuations, but then what happens is something quite surprising, at least not with insight, that the 2 lasers are mod locked, but they are fully synchronized. You can see the peaks correspond perfectly to each other. This is called synchronization, and that's fundamental in order to get these coherent Raman measurements. With insight, this is kind of obvious, but the advantage is that we can then put $1 million system on an optical table, actually in a shoebox, very cheap shoebox that you can even shake because it's based on optical fibers, and then you can use it to do measurements. Let me skip some of the technical details in order to do broadband, but let's look at the tests. So these were initial tests with polystyrene and PMMA beads, and they have different Raman signal, and you can see the beads, the other bead, and then you can distinguish the two. And this is other chemical compounds, but what is more interesting here, this is a tumor model, is a mouse fibrosarcoma. This one is the typical stained slice that a doctor will do, where you have the cancer, the healthy connective tissue, and then you can take the system and do this label-free stimulated Raman scattering. But because it's Raman, the map is now not just a morphology, but it's a spectrum. So you can do cuts at different frequencies and identify different types of chemical compounds. And for example, you can identify the cancer from the healthy tissue very easy. And these are other examples, so I don't go to the details also because the time is finishing. But for example, this is the complete picture. But then you say, I only want to see the lipids. And you press a button, and that gives you the map only of the lipids because of the way Raman works. You want to see only the proteins. You press a button, you only see the proteins. This is not possible with histopathology. So now the next step is then to, because the amount of data that we get is huge, you need to implement AI in order to analyze all of this data and create an outcome. So, and let's look at this picture. This is a stimulated Raman scattering picture. This is a AI stain picture, and this is the H&E stain picture. So it means that the AI is producing an image out of the Raman that looks similar to what the doctor sees when they do the staining. And whenever we show this without the labels at the top to doctors, they were unable, most of them, to distinguish which one is the AI stain and which one is the H&E stain. Also, and the final point here, if you look closely at AI on Raman or the pathologist annotation of tumor or not, the blobs look similar, but they are not exactly the same. And this tells you that, of course, we believe that Raman gives you some additional information that the eye and brain of a doctor without any objective tool will not be able to give you. So this can also be used in pharmaceutics. This is an interesting example. These ones are pictures of the same drug produced by 6 different companies. And if you do the mapping, you can see that while the contents are similar, the composition, the dimension of the grains are different, even though in principle it's exactly the same drug by different companies. So where are we with this? We started a company called Cambridge Raman Imaging 3. And from the lab experiments, we now have a laser that is on sale. Already 3 systems were sold, and now is in the market. We also have a multi-channel lock-in amplifier that is called CHAMP. This is also on sale. And soon, in the next few months, the entire system with a microscope and software will be put on sale for people to use. And with this, I will stop here and acknowledge the funding from the Graphene Flagship and many other funders, and all the collaborators that helped for this work, in particular, Giulio Cerullo, Dario Poli, and Matteo Negro for the Raman work. Thank you very much.
Thank you very much, Professor Ferrari, for this impressive talk and webinar. I think we have some time more for some questions from the applicants for the school. Let me check a bit the chat. So,
Hi.
Yes.
Can I ask?
Okay, start. Okay, you can make a short question. Yes, please.
Yeah, thank you, Professor, for your nice presentation. That I have just one query. That when you are shows that the graphene ink is screen printed on glass, on the white paper, what is the motive? Because this silver paste and other paste are there.
I didn't quite get the question. You're asking me if we also use silver paste? No, there was no silver paste, but of course we can also do both. And for example, we have a paper coming out soon where we use both a graphene ink and a silver paste together because of this was making things easier. But in principle, you don't need to use any silver.
But graphene, if we are consider about the cost, the graphene is highly cost compared to silver paste or copper.
Absolutely not. Absolutely not. Graphene costs like water, basically. The cost of graphene is very, very small, and certainly smaller than the cost of silver. And the point is, if you make it in the lab by yourself or you buy from some of the catalogs online, yes, it's very hugely expensive. But if you go to a company and you buy a ton of graphene ink, you will find out that the cost is very small, and definitely smaller than silver ink. There's no. This is in 2024. It was not the case in 2009, but now it is the case.
Okay. Thank you for your clarification.
Okay.
Thank you. It's
Thank you. Thank you. So let me read a question from the chat from Mr. Thanos Styliakos. He's asking about graphene-based filaments for 3D printing. Okay, this is a very big question, but so he asks about what are the basic polymers, PLA, ABS, that are used for graphene-based filaments for 3D printing, and at what loadings?
So different people use different polymers. For example, now we have a project to 3D print the scaffold of nanocube satellites, and we are using PEEK. And the loading is a few percent. So, I mean, this is an old story. I mean, 3D printing, we did it over 10 years ago, something like that, for the first time. So it's quite common. There are companies selling filaments, and it takes time to develop a new filament, but it's always basically successful. So it really depends what you want to do. And the loading depends on, do you want to have only mechanical properties, or do you need some electrical and thermal properties or something like that? But typically is of the order of a few percent. But it can be much higher. If you go to very, very high loading, what happens is that the filament, they become brittle, and they don't really work very well. So you need to be, it depends on the polymer you want to use. It depends on the application you have in mind. And it also depends on the printer that you're using. But it's all quite standard now.
Also, Thanos asked about if they can be used as printed, or they should undergo a thermal treatment to evaporate the polymer before you use them. So,
what do you mean, the inks?
Yes, the filaments. Yes.
The filaments. No, the filaments, at least were the ones that we make them in-house. So we do all the process in-house. I actually have never bought a filament from a company of the one selling 3D printed graphene filaments, so I have no idea what you need to do with them. But in our case, of course, we need to use different processes, including thermal treatment, when we use the ink to make the filaments. But what we're trying to do is to also change the solvents or even use water instead of any solvent in order to create the ink. So all of this is based on the chemistry and also the functionalization that you do in-house. Once the filament is ready, we don't do anything else. We put it in an extruder or in the 3D printer. But of course, there is a lot of work done in order to, I mean, a lot. It depends what the definition of a lot. It takes a few months to develop the recipe, but once the recipe is developed, it's very easy to do it. You repeat it all the time.
Okay, thank you very much for your reply. I cannot see any other question. From my side, I would like to make a general question about to make the link with the responsible electronics, let's say, topic of the school. Very impressive progress in the last years about graphene and related products and applications. What is the benefits of using these materials in relation with the environmental impact, and in general with the framework of responsible electronics? I mean, how much more green, let's say, are compared to silicon-based technologies or other materials?
This is a question for me. I mean, you should
Yes.
be able to answer the question, because
Yeah.
we, of course, believe that they are greener for a variety of reasons. But you need to be careful, because usually what is not green is not the graphene, but is the solvent that you're using. For example, you may not want to use NMP and so on. You also need to consider the source of the graphite. It can be natural graphite, but actually there are some graphites that are coming out as the byproduct of steel production, and this clearly is helping the environment when you use them. And at the moment, there is a recyclability that you can use, that you can do when it comes to graphene. You can actually burn them off and take the ashes and use them again at the end. So there are lots of advantages there. And since you mentioned this, and you also mentioned in the introduction of the Graphene Flagship, it's very important to mention this new initiative called Innovative and Advanced Materials for the EU. This will replace the Graphene Flagship. The Graphene Flagship will merge with this and will start in 2025. And safe and sustainable by design material, life cycle analysis, and printed materials and so on will be at the center of some of the activities in this area. So there will be a huge push to have SSBD, safe and sustainability by design, LCA, life cycle analysis, and so on. But at the moment, everybody, at least most people, agree that the graphene can be considered safe and for this application. Also, there are some question marks on the health implication of, for example, silver inks and so on. But I don't want to go into the details now because I'm not the expert here.
Thank you very much. So thank you very much for your participation, Professor Ferrari. Thank you very much. So now we can proceed to the
Okay, thank you. Bye.
The second speaker of today. So I think we have Giovanna with us. So Giovanna, if you hear me, you can share your screen. And okay, great. So few words about Giovanna before starting. I give you the floor to Professor Milic, Giovanna Milic. Giovanna will speak today about multifunctionality of layered hybrid perovskites for emerging nanotechnologies. A few words about Professor Milic. She's an assistant professor and Swiss National Science Foundation Prima Fellow at the Adolf Merkel Institute of the University of Fribourg in Switzerland since 2020. Her research is centered around the development of hybrid and stimuli-responsive supramolecular materials for energy conversion, with a particular interest in photovoltaics. This has been recognized by several honors and awards, including the ERC starting grant in 2023. She will be taking on an associate professorship in materials chemistry at the University of Turin in Finland from September 2024, continuing her research efforts toward the development of smart and sustainable nanotechnologies. So Giovanna, thank you very much for accepting our invitation to give a seminar in med school. The floor is yours. Thank you.
Well, thank you so much for this kind invitation and introduction, and for organizing this school. It is really a wonderful initiative, and it is a great pleasure to contribute and have the opportunity to exchange also online on this occasion. So it is further my pleasure to share with you some insights on this multifunctionality of layer hybrid perovskites, which might be relevant in the context of this school, as it has been an important topic in the context of photovoltaics, but it becomes increasingly relevant for a variety of emerging nanotechnologies that I hope to outline today and open the discussion on, while sharing some insights on our ongoing research developments, while stimulating perhaps ideas and interest in some of the future perspectives. Now, this research has been primarily conducted at the Adolf Merkle Institute of the University of Fribourg in Switzerland, where I have the privilege of leading the Smart Energy Materials team since September 2020, with the generous support of the Swiss National Science Foundation, as well as a number of national and international partnerships, some of which I highlight here, including those of the Swiss leading house for Latin American region and South Korea, as well as NCCR bio-inspired materials, along with EPFL, with whom I remain affiliated, as also co-supervising a number of young researchers. Now, overall, we are gathered around this shared vision, or to an extent overreaching objective, to control complex molecular assemblies in order to address a specific function across length scales, from the molecular to the material, all the way to a functional device level, with the purpose of developing smarter materials that can respond to different external stimuli and adapt to their operating conditions, even in functional devices, such as those for energy conversion, as in photovoltaics. Now, to proceed in this direction, we often find inspiration from, well, nature and biological systems that offers much more adaptive solutions and a variety of responsiveness to different external stimuli that are very apparent across biological processes, such as those in natural photosynthesis, for instance, which has greatly inspired the development of a number of artificial systems for energy conversion, as those in photovoltaics. Now, this often involves the role of a specific toolbox in the form of supramolecular chemistry, or chemistry of non-covalent interactions, that are at the core of enabling some of these adaptiveness in a variety of biological processes that also stimulate and are at the core of our research pursuits, that evolve around this question of whether we can truly repurpose some of these non-covalent supramolecular interactions in order to address a variety of challenges associated with artificial technologies for energy conversion, while enabling the development of such smarter or more adaptive nanotechnologies. And for this purpose, similar to the natural systems, we neither rely on organic or inorganic systems entirely, but rather they're hybrid organic, inorganic materials, or so-called, in particular, framework materials that enable realizing some of these dynamic and stimuli responsive functionalities, even in the solid state, that is especially relevant for the development of functional devices, and it's those in photovoltaics as well as beyond. Now, in general, for the purpose of a broad audience, these framework materials are very generically and schematically defined by these units comprised of often inorganic nodes connected by typically molecular linkers that provide the opportunity for enabling these dynamic functionalities even in the solid state that go beyond just vibrations or random molecular motions, all the way to more restricted, controlled, or even directional motions across length scales, from the molecular to the unit cell, all the way to the extended framework level and their assemblies. Across different framework material classes, which often are associated with the conventional metal organic frameworks or covalent organic frameworks, but in fact also include classes of materials such as zeolites or metal halide hybrid perovskites that are, unlike other dynamic framework materials, in fact, to a greater extent, softer materials, and at the same time, featuring optoelectronic characteristics that are much more compatible with modern optoelectronic technologies that really stimulate then our research focused on this particular class of materials in this context. Now, in general, they have been particularly utilized in the context of photovoltaics, as some of these the attendees are well familiar with, and especially the perovskite solar cells, which have emerged over the past a bit more than a decade. And in this period of time, already managed to challenge some of the conventional photovoltaic technologies in terms of their performances, while more importantly offering much more cost-effective and solution processable thin film photovoltaic technology that stimulates this unprecedented interest in this research community, but also beyond. And this is associated with the unique optoelectronic characteristics of this metal halide perovskite active layer that is defined by this cubic crystal structure typically, and the AMX3 formulation that represents such a corner-sharing octahedral framework comprised of divalent metals, typically lead or tin, and different halide anions that otherwise within this framework host the central A cations that can be inorganic, such as cesium, or small organic moieties like methylammonium or formamidinium, which in fact render these systems now hybrid organic inorganic materials. Now, what makes these systems so fascinating, apart from their incredible utility in optoelectronics or photovoltaics, is that these now hybrid and crystalline ionic materials are at the same time soft and dynamic materials that feature even mixed ionic and electronic conductivities, as well as the capacity to adopt a variety of dimensionalities that is especially relevant for this contribution to the seminar, and that offers an important platform for such function-driven material design and smarter functionalities in a variety of framework materials and nanotechnology. Now, these attributes already set the basis for the multifunctionality of these materials in the context of a variety of their applications, from photovoltaics through light-emitting diodes, photodetectors, sensors, and many others, including in particular also flexible technologies where they provide additional advantages. Well, at the same time, unfortunately, the same characteristics are to an extent related to, well, one of their major challenges, which is in fact their limited stability across different device purposes and architectures, leading to the performances in these systems to gradually decrease over time, especially when exposing these systems to external environmental factors like oxygen or moisture, but also as a result of these internal ion migrations related to their mixed conductivity that are accelerated under different operating conditions, including temperature changes, light, or bias, and which leads to a number of degradation processes that pose an ongoing challenge in this research community, challenging also their further developments and applications. Now, in the face of that particular challenge, we could rely on this unique supramolecular toolbox to address it by utilizing a variety of these non-covalent interactions that are here schematically represented, and whose now versatility, but also adaptiveness, enables not only addressing this challenge, but also designing a number of functional materials and perhaps smarter nanotechnologies, and which becomes very relevant in the context of metal halide perovskites, as it enables now tailoring these different interactions between complementary underlying organic and inorganic components inside the hybrid perovskite framework, being either in the precursor solutions and elements for their formation, or the resulting solid state structures, such as by designing small molecular modulators that can interact with the surface of hybrid perovskites, now templating their structure and affecting their overall functionality that can be translated ultimately from the molecular level to the resulting device operation. Now, in terms of this functionality, this involves a variety of different aspects that can be controlled in this matter, including the morphology of the resulting materials, which is important in the context of the relevance of supramolecular chemistry and crystal engineering, and the importance of morphologies for the resulting material performances and device operations through defect chemistries, or ultimately stability of these systems under different operating conditions in the functional devices. Now, this, as an example, illustrated here, can be monitored by analyzing these, the resulting solar cells in presence and absence of different modulators, and continuously radiating them over time, as illustrated here by monitoring their power conversion efficiencies over time and comparing the treated systems in red to those that are the conventional perovskites in blue, where we see that the benefits of using or relying on some of these systems to ultimately stabilize their performances over time, even in perovskite compositions such as those known as formamidinium lead iodide perovskites that are very attractive for the resulting, for the purpose of their optimal optoelectronic characteristics, but notoriously unstable, where we can further highlight the benefit of relying on some of these approaches. Now, this is possible by analyzing these systems systematically in both perovskite thin films and mechanosynthetic powders that are either prepared through solution processing, very straightforward approaches such as using a solution-based spin coating followed by annealing to remove the residual solvents, or fully ball milling the precursor elements to form the resulting materials that can be then analyzed by a series of complementary techniques to identify some of these effects, as the one that I very briefly illustrated, which involves in turn a combination of different theoretical and experimental techniques, which are briefly outlined here, including both the techniques that involve the analysis across different lengths and time scales, including theoretical methods that we often rely on through collaborative efforts, and amongst which I would like to particularly emphasize the role of different X-ray diffraction techniques important for these solid-state crystalline materials, but also solid-state nuclear magnetic resonance, or NMR spectroscopy, that is especially important for the understanding of these atomic level interactions that are relevant in the resulting functionalities and the effects. Now, this now enables revealing some of the key factors that are responsible for enabling such supramolecular level controls in these systems, which can be summarized as the role of different non-covalent interactions and their templating effects in terms of the resulting structure, which I would like to focus on today by outlining some of the examples of how these strategies can lead to other hybrid emerging structures, as well as their emerging functionalities that even go well beyond photovoltaics. Now, in general, these were enabled by providing intricate atomic level understanding of the nature of the interactions between the underlying components, which have set the basis for going beyond the use of these small molecular modulators at the interface with hybrid perovskites, often in substoichiometric amounts, to fully incorporating them now within the extended hybrid perovskite frameworks, such as by building these layered, or in this case, two-dimensional, often low-dimensional or layered, here represented two-dimensional perovskite architectures, where now the organic layer serves as a spacer templating hybrid perovskite frameworks through either these monofunctional organic bilayers known as rootless and pauper phases that are much more conventional for these layered hybrid perovskite systems, leading to a slight half a unit cell offset between the inorganic slabs, or this bifunctional organic monolayer forming such so-called Dion-Jacobson phases with well-aligned perovskite slabs. In both of these cases, contributing importantly further to addressing one of the most pressing challenges, which is their stability, through both the hydrophobicity of the organic component as well as their ion impermeability, while at the same time enabling these tailored systems to more directly contribute to the resulting properties of the materials through careful tailoring of the interactions between the organic components. Now, so far, in these systems, this has primarily involved relatively simple organic molecules that can template such layered structures, which can be represented by these two archetypical structures primarily used in the rootless and pauper phases that are predominant, being this butyl-ammonium system, so having this ammonium termini to anchor to the inorganic phase with the alkyl chain that forms this, organic layer templating the rest of the system, or this phenylethyl ammonium system that enables the same through further tailoring the interactions through some of the pi-based interactions of the aromatic system. Now, these and many other of the organic spacers that have been used in this context are primarily highly accessible off-the-shelf systems that enable accessing some of the rootless and pauper architectures, but which we ask ourselves whether it will be possible to further tailor to better control these assemblies and access additional functionalities. And for this purpose, we have expanded the scope of these systems, such as by tailoring further the underlying interactions, such as the van der Waals interactions based on these alkyl chains, by strengthening them through the introduction of such carbocyclic elements in different adamantyl-based systems, or functionalizing these simple aromatic systems by, for example, shortening these alkyl chains from these ethyl linkers to shorter methylene ammonium-based systems, and introducing other functionalities to access the corresponding Diane-Jacobson phases that are not as prominent in this research domain, comparing them to the rootless and pauper systems, and further expanding their scope by introducing additional aromatic units or other functionalities, such as, for example, different heteroatoms in the form of also perfluorine-based aromatic modification that would then change also the polarity of the aromatic group, enabling now more robust pi-based interactions with within this organic component that further strengthens also increases their stability, makes for more robust structures, and enables understanding better some of the gauges that can be used to tailor their structural properties and also the emerging functionalities, which overall highlights the powers of this unique supramolecular toolbox to not only now address the pressing challenges, but also introduce or use them to introduce additional functionalities in these systems, such as through this uniquely tailored organic component, which can now no longer play only the structural templating role in the resulting materials, but serve an additional purpose in the resulting, for example, optoelectronic characteristics. Now, in general, the systems that I have previously outlined with their corresponding organic spacers primarily involve electronically inactive, or rather insulating organic components that lead to these systems to often behave as natural quantum wells, as the optoelectronic characteristics are primarily defined by the metal halide orbital overlaps that ultimately define different optoelectronic properties, including their corresponding band gap, while the organic component serves more a structure templating role without a direct contribution to the optoelectronic characteristics, leading to then consequently the charges to be primarily confined to the inorganic layer, while the organic system merely indirectly controls the resulting structure and the corresponding properties, which can be further tailored, for example, by introducing other organic systems that have complementary, more electroactive characteristics that can contribute to these systems beyond just structured templating roles, such as by tailoring their energetics to have more direct contribution to the overall structure in the so-called inverted quantum well architectures that can be achieved by introducing different organic components that can act as electron donors or acceptors, as illustrated here by one of the representative examples that we have relied on, including this electron accepting naphthalene, the image functionalized unit for accessing now Diane-Jacobson architectures, which possibly additional functionalities. Now, with incorporating such systems in the extended Diane-Jacobson like architectures, one can stabilize the resulting structures even in these notoriously unstable formamidinium lead iodide systems, as illustrated by this solid state NMR spectroscopy, and in this case nitrogen 15 NMR, indicating in presence of these spacers and in the layer systems the stabilization of this desired perovskite alpha formamidinium lead iodide phase. Now, more importantly, in these materials, Apart from the structural level interactions that enables this stabilization, the electronic interactions and exchanges were also particularly relevant, which were analyzed by using transient absorption spectroscopy that here reveals the emergence of this signal around 550 nanometers, which in fact, particularly upon excitation at around 500 nanometers, that in fact corresponds to a naphthalene diimide or MDI radical anion, which cannot be generated upon excitation of the neat organic component under these conditions, and which in fact requires this electronic exchange between the inorganic and the organic phase for it to actually appear in the hybrid structure, suggesting that this is in accordance with inverted quantum well architectures where there is a more direct exchange between the organic and the inorganic component, and which now sets the basis for relying on these systems in alternative functional roles that not only involve this active absorber inside these conventional solar cell architectures where these systems are typically sandwiched between different selective charge extraction layers, but also taking perhaps the role of some of these charge extraction layers in addition to their stabilizing role. Now, overall, this sets a nice example to illustrate some of these multifunctionalities that can be accessed in these systems beyond the structure directing role that not only involves electroactive components, but also other stimuli responsive systems, including those responsive to light, including different chiral moieties, or pressure as another important physical stimuli, or the associated strain that is especially important for the utility of these systems in a variety of different modern technologies, including those of the flexible device architectures. Now, to probe the capacity to rely on these systems and their adaptiveness to different external strain, it is worth emphasizing why understanding the effect of strain is very important in this context, as it can also offer a unique gauge for tailoring the properties of these systems without, in fact, changing their chemical composition. This strain could lead to changes in some of these, for example, metal halide orbital overlaps as a result of changes in the bond lengths or bond angles, which will then directly be reflected in the changes in the resulting optoelectronic characteristics. Now, this has been previously demonstrated on a number of occasions, which, however, involves relatively high pressures above around 5 gigapascals or even towards 10 gigapascals, which leads to beneficial changes such as reducing the band gap or even metallization of these systems, but which often leads to changes that are irreversible and also often with such high pressures, not very practical for functional device applications. So this is where these hybrid systems, including larger organic components like layered hybrid perovskites, might provide the opportunity to rely on some of these additional degrees of freedom in softer materials to reduce the pressure ranges, which we can access some of these changes through additional reorganizations within the spacer layer, for example, through their different penetration into the inorganic layer, different orthohedral tilting, or rearrangements directly within the organic layer as a result of the compression that would then directly be reflected in the resulting optoelectronic characteristics of the layered hybrid material as well. Now, to assess the capacity to do this, while at the same time doing it reversibly in more adaptive systems or smarter nanotechnologies, we have analyzed both Rudolph-Popper and Dion-Jacobson analogs or model systems to illustrate this that I would like to share briefly with you. And we have also focused for this purpose on a relatively low pressure range up to around 0.35 gigapascals, which in fact corresponds to the level of strain that is more comparable to the strain that can be induced by some of these structural rearrangements within the spacer layer. Now, and for this purpose, we have relied on two relatively closely comparable model systems that involve both Dion-Jacobson and Rudolph-Popper architectures that incorporate these simple aromatic units functionalized with these metal ammonium linkers, being either this benzyl ammonium for Rudolph-Popper bilayer phases or this phenylene dimethyl ammonium in the bifunctional spacer moiety for such Dion-Jacobson architectures, both of which in thin films form these well-defined layered structures which can be easily captured by their corresponding X-ray diffraction patterns, leading to these nicely clear periodic patterns indicative of the formation of the layered structure, often preferentially organized parallel with respect to different substrates. In both of these cases, showing also larger d-spacing for the Rudess and Popper architectures as compared to the Dion-Jacobson ones, and the smaller spacing for the bromide-based systems as compared to the iodide ones, unlike in the surprisingly benzyl ammonium-based case when this trend is inverted, suggesting also a slightly different assembly in the bromide-based benzyl ammonium system within these materials. Now, when exposing these well-understood layered perovskite architectures to external pressures, we can notice that these structures change across all the lattice parameters that are slightly compressed, especially along this A-axis that particularly corresponds to the corresponding spacer layer, and which is most pronounced for this unusual assembly of the benzyl ammonium lead bromide-based system that was in fact found to be the only system amongst those analyzed that is fully non-centrosymmetric, making it more susceptible to some of these external changes in response to pressure. These changes, interestingly, which were analyzed in collaboration with our colleagues in the group of Nicola Cassati at PSI, but also Bruno Erla at AMOF, as well as the Ursula Rötschlichberger at EPFL theoretically, they could be theoretically predicted by analyzing the behavior of different structures under pressure and monitored experimentally with respect to their changes in the optoelectronic characteristics, both the UV-vis absorption and photoluminescence emission, which in case of these layered perovskite systems typically feature these conventional excitonic peaks that then redshift upon exposure to higher pressures to an extent that is most pronounced for these systems suffering from or tolerating the highest structural rearrangement as this Rudess and Popper benzyl ammonium lead bromide-based system. Now, most importantly, in the context of this study, these changes that are apparent for all different layered perovskite compositions are also found to be fully reversible within this pressure range, which means that the system reverts to its original configuration when reducing further the pressure, highlighting now the potential for the first time of these layered perovskite systems to feature such reversible mechanochromism that enables tailoring the optical response of these materials in response to the strain, such as in the form of external pressure, but in the pressure range that fairly corresponds to the level of strain that can be triggered by different internal structural rearrangements, which offers now the basis for relying on these systems as potentially amphi-dynamic scaffolds for controlling different stimuli responsive dynamic systems, even in the solid state, and well beyond photovoltaics. Now, this importantly opens a new perspective for tailoring these systems in response to alternative physical stimuli, which can be triggered through the changes in the organic component, including those that involve light as a stimuli that would offer the possibility to perhaps design smarter solar cells that are more adaptive to different light intensities or even the corresponding day-night cycles, which often involves the control that is associated with different ionic motions that can be accelerated or in response to light or bias, and which, as it's already known in the field, involves a certain level of reversibility of the ionic motion in the dark that is responsible to some of the recovery of the devices and their performances when exposing them to darker conditions or reducing the light intensities. However, this still involves a certain level of permanent degradation that is associated with some of the ion migration, which poses a question on whether we could really control this process by enabling some of these beneficial recoveries or reversible motions of the ions without, or by suppressing some of these permanent and undesirable degradations, which we have explored by relying on a number of different photochromic systems, one of which are illustrated here very schematically, showing that this is possible to achieve even in the solid state by and under the conditions of mimicking the performances of the solar cells with or their changes with the day-night cycles. That opens now the perspectives to tailor these stimuli responsive systems more effectively in even adaptive solar cell architectures. Now, overall, this also sets the interesting basis of and perspectives for controlling some of these processes and utilizing them even beyond photovoltaics, especially when it comes to the level of understanding of the changes that are associated with the underlying ionic motions that are often the factor that contributes to not only their stabilities or instabilities in the context of photovoltaics, but additional functionalities that may go beyond where ionic motion might be beneficial. And this might offer the opportunity to design technologies that are even smarter in the sense that they can also mimic, as smart at mimicking our human brain, such as those that can act as memory elements or so-called artificial synapses. That is an emerging discipline and perspective that stimulates a number of research interests. Now here, nature once again provides a very powerful example of very efficiently for processing information and memory in a single unit, which is our brain, by utilizing effectively the underlying components or neurons, and in particular through the functionality of the synapse between the neurons, involving again tailored molecular components or neurotransmitters that affect the ionic motions within the corresponding synapse that are responsible through opening or closing of different ion channels to triggers a specific action potential or the electrical impulse that provides a stimuli for controlling a number of processes in our bodies or different functional organisms, where poses a question of whether we can really effectively mimic this process in an artificial system that can enable now this effective information processing and memory storage through ionic control of these ionic motions. Now, hybrid halide perovskites here provide a unique opportunity to address this by relying on their mixed ionic and electronic conduction that can, through certain voltage biasing in relatively simple device architectures, contribute to the formation of conductive filaments based on either ions or the corresponding vacancies that can, to an extent, mimic the process in such resistive switching systems where the conductive filament can be set at a certain voltage, forming this lower resistance state, or reset at another bias where the rupture of the filaments lead to a higher resistance state through a process that forms a so-called resistive switch mimicking, or that can act as a memory element to providing different memory states that can be tailored to mimic perhaps some of the natural systems. Now, to explore this, we have ventured into this arena through a great collaborative effort, utilizing some of the layered perovskite systems that in relatively simple architectures, when they're sandwiched between a conductive glass and a metal contact, such as this aluminum-based contact, exploring these relatively simple and previously outlined aromatic-based rudolph Popper and Dion-Jacobson phases, whose now voltage bias, current voltage characteristics upon biasing within the range of this -4 to +2 volts, show characteristics that resemble some of these resistive switching properties, which involves in particular, when sweeping between the 0 and 2 volts, the appearance of this set process leading to the low resistance state that is much more abrupt when using counter ions in the form of bromide as compared to iodides, where we have a more gradual change to this lower resistance state, suggesting the contribution of the ions to this process that can be controlled then through a number of cycles for both the set and the following reset process that would then take place more around -1 volts triggering in both cases of the bromide and the iodide system. Now, importantly, this switch between the low and the high resistance state through the corresponding either gradual or abrupt set and more gradual reset process in these systems can take place over a number of different cycles, several hundreds or cycles in particular, where the reliability of these cycles is further analyzed by looking into their retention as well as endurance over a number of these iterations, where we can see for both the bromide and the iodide counter ions having a distinct distinction between these two states, being the low and the high resistance states, with the on-off ratio of around around 10 to the 2, where we can see the retention time for each of these states in the order of around 10 to the 4 in both cases, and endurances over cycles that are more than 120 cycles. This is important to compare the behavior of these systems to some of the existing technologies and to offer the example of their potential that can be further tailored depending on the material class and also the corresponding device architectures. To test their applicability in that regard, or the potential for this applicability, our collaborators have also used them in these data storage and retrieval cycles, in particular the write, read, erase, and read cycles that are commonly used for probing these behaviors, using, for example, the biasing or the pulses at 2 volts for 4 seconds to write information, followed by small pulses of around 0.2 volts for 6 seconds to read the information, erase them at around -4 volts for 4 seconds, and then reread the input again at 0.2 volts for 6 seconds, which has been done over 100 cycles with relative voltage uniformity, having these set voltages of around -0.143 volts, and the set of around 1 volt, where you can see here distribution that is very important for the reliability of these systems, showing some potential of tailoring this further. Importantly, this is illustrated for both the bromide and iodide counterions, but the difference that you have seen at the beginning with these more abrupt or gradual changes that depend on the migration of the corresponding ions were also reflected in the differences in their behavior under these voltage pulses that were further probed to assess this synaptic behavior by exposing them to specific voltage pulses over time that for iodide-based systems show this characteristic behavior of the gradual buildup of the conductance or potentiation, or the gradual depression that to an extent mimics some of the behavior of the natural synaptic behavior that offers now the perspective of these systems to serve this purpose perhaps in the future. And illustrating here how this can be done in a manner potentially where not only the switching of the behavior enables the memory response, but we can also switch these systems to different counterions to have the behavior that is more abrupt or digital or more closer to the synaptic one expected for these systems for utilizing them in such memory elements in the future. Now, overall, I hope that this provides you with a brief overview of some of the capacities of these supramolecular controls in these hybrid materials to stabilize them, address their performances, but also potentially advance them towards more multifunctional platforms for smarter nanotechnologies. Now, I would like to emphasize that this opens the path to us further perhaps realizing this objective of better controlling these devices and underlying materials through the intricate understanding of their supramolecular assemblies between the organic and the inorganic components that are also controlled by the tailored molecular systems at the core of these functionalities, and through which we can set the basis for advancing them towards perhaps smarter nanotechnology. Now, with that, I would like to first thank all the colleagues and collaborators who have in different capacities contributed to some of the work that I have shared with you today to stimulate further discussions and provide more insights into the capacities of these approaches, including the current and the former members of the Smart Energy Materials team, our funding agencies, and a number of collaborators, such as those at EPFL, from the group of Professor Michael Gretzel, Lyndon Emsley, Ursula Röschersberger, and until recently, Jacques Moser, but also a number of others across Europe as well as worldwide that I highlight here as they have contributed to some of the projects that I have emphasized today, amongst which I particularly highlight the groups of Nicola Cassati and Bruno Ella for their contribution with analyzing some of the pressure-induced changes, the advanced structural changes, and the optical properties, as well as those of Mahesh Kumar, who have opened this new chapter of analyzing some of these systems in the context of their potential with memory elements. And in general, who these interactions also further strengthen really my belief in the importance of these approaches, especially cross-disciplinary approaches in addressing some of these complex contemporary challenges, while opening the path for perhaps more innovative technologies as well. With that, I would like to thank you all for your kind attention. While I very much look forward to our discussion, hopefully leaving more time to exchange about the details of some of these approaches. And if you allow me, just as a follow-up to your kind introduction on the ERC starting grant, I also use the chance to invite those who might be interested in some of these topics to consider applying to our team, as we are currently hiring to continue some of these exciting research activities. Well, with that, I thank you all once more for your patience and kind attention, and look forward to our discussion. Thank you.
Thank you, Anna, for this very nice presentation. I would highly recommend to apply for a position in your group. So
Thank you very much.
I think you are moving now in Finland for your
That's
ERC.
right.
Okay.
Although the Swiss team will continue to operate, so I will continue to work across two institutions for quite some time now.
Great. So please, is there any question from the audience or from the chat, or we can take the floor and ask directly?
Let me see.
We have a comment from Salman that he's working on perovskite materials and he's excited about this. Any question regarding the layered perovskite materials and their applications? Meantime, I can ask about. Okay, so the topic. I'm
just checking the comments. I see that there are some. So thank you all for leaving the comments. I appreciate it. Thank you. I do not see the questions though, but maybe you have them.
Not yet. Not yet. Meantime, I would like to ask you about the topic. The topic of the school is disposable electronics. So we have a comment from Maria. Maybe it's better from audience to ask directly. So my name is Dr. Maria from. I have a question about the formation of the filaments within the memory store. So if I understand well, if it is local formation.
Yeah, I guess so.
Or a surface, something like that. Yes.
That's my understanding too. So from my perspective, so we localize these basically by relying on specific contacts in a device. I'm not quite sure. I guess the question here might more rely to the mode of operation where the filament actually corresponds to a specific metal mediated filament formation or all general ion mediated formations. I invite maybe the person who left the question to also engage in the discussion. But in terms of localizing, I wouldn't be able to discuss this in terms of the specific localization of the. Is it centered or spread on the surface? I would argue that it is spread across the surface and that it's very difficult to localize them, especially if they correspond to ions or the vacancies. I think for mechanisms that are more relying on the redox activity of the, for example, metal contacts that contribute to the filament, this is maybe perhaps more easier to localize in terms of monitoring the formation of the filament. But so far, to the best of our knowledge and level of understanding of the behavior of these systems, they are rather taking place through different surface areas.
I think we have another question now from Mr. Khalid. Maybe you can read it. He asked about the stability. How we can extend the stability.
Yeah, this is a wonderful question. Thank you for bringing this up. I think that many of these works emerged from the interest in the understanding of hybrid systems, but also the potential of the supramolecular approaches to stabilize them at first. However, the stability of these layered, especially in the case of layered-based systems, offer perspectives to enhance their functionality as well. I think this is an interplay of factors at the moment, while in the future, I believe that it will be more possible to stabilize them and ensure longevity by leveraging on their multifunctionalities. You got a hint on some of these through their light responsiveness, as the objective is not only to change the property, but to essentially stabilize it through the multifunctionality in response to light. So I think the two are closely interrelated, and I think that the layered hybrid perovskites offer a unique platform where we can leverage both functionalities, essentially the stability and additional stimuli responsiveness.
Thank you. There's another question about MOFs.
About MOFs.
Oh.
This is so we're currently not working on metal organic frameworks, but I put them into context because when we talk about framework materials, we often think about metal organic or covalent organic frameworks. So zeolites or metal halide perovskites are also framework materials with different characteristics, and as such can be compared to MOFs or COFs for different benefits in different contexts. So some of the linkers, however, that are relevant in MOFs are equally relevant in especially layered hybrid perovskites. So there are synergies also between these two fields. So we follow the developments and learn from them in different contexts, but we do not use MOFs at the moment. Thank you. They're much more rigid materials and not as compatible with optoelectronics as much as we would like them to be. At least at this moment. Also, although there are wonderful developments on electroactive MOFs as well.
Okay, thank you, Joanna. Any other question? You can write in the chat. So just to continue my previous question about the school the topic of the school that is responsible electronics. So what is your comment about the, let's say, environmental impact of this kind of novel layered materials in terms of toxicity or about the solvents that you have to develop them in specific solvents? Are these solvents green or toxic?
This is a very important question. I'm glad that you take it at the heart of the workshop as well. So there has to be efforts to move to less toxic systems. So far, most of our materials are lead-based. So all the systems I discussed are lead-based, and this is a major issue for the general environmental impact of these materials. This is why I'm pleased to share that the ERC project starting from this fall will exclusively focus on lead-free materials in a number of these applications, which I believe needs to be one of our efforts to replace these. In parallel to working on different effective encapsulation techniques or complementary functions that can prevent some of these environmental impacts should the issues come into play. As when it comes to the processing of these systems, so of course they provide advantages in terms of using lower temperatures to process them as compared to other semiconductors, but solvents can also be a major issue. This is where the soft nature of these systems offers an exciting perspective for using mechanosynthesis to form them in completely solvent-free environments. And I can tell you, based on all our analysis so far, it has been a very effective approach to accessing a variety of different layered or conventional three-dimensional perovskites that we use regularly for the purpose of primarily analyzing higher quantities of materials, such as by NMR, that is not a very sensitive technique, but at the same time preparing these systems mechanosynthetically and depositing them through other approaches might be another way to avoid some of the solvents. Finally, I think we all need to be much more mindful in terms of what solvents are being used. DMSO, surprisingly, is a solvent with a very low environmental impact. DMF, that is another common solvent used, has a lot of dangers associated with it in terms of toxicity and more detrimental impact. But we can be more mindful to focus on solvents that are not overall detrimental to the environment. And I think initiatives such as this one, or the one just mentioned previously in Europe, such as Safe and Sustainable by Design, that should become a norm or should be part of all of our pursuits, are a great way to be more mindful from the very beginning of the project.
Okay, thank you very much. I have received some private messages about how they can contact you if they want collaboration. I think you can send directly an email to Professor J.Milic and ask her about the collaboration or application for open positions that are in their group.
Yes, please reach out by email, by different social media, I emphasize,
LinkedIn, yes,
and also follow some of our activities through our website.
Yes, and Sashi is asking about how many devices have you tested for neuromorphic memory applications, and just a comment about variability and reliability.
Yeah,
I think we will.
I think there were some hints on this variability also for the voltage, not also over the cycles, but also over the number of devices. So I don't have a precise number, but these are tens, 20, 30 devices or more, depending on the different projects and initiatives, which is very important because this is the main issue in this field, similar to the solar cell. Performance is even more pronounced in my view. This is what frankly delayed a lot our contribution in the field. We have been working on the topic of mixed conduction and trying to use these approaches, memory elements, is roughly 2017, 2018. But many of these approaches were not very reproducible. We did not understand well the impact of the, for example, size of the contact, the impact of the sizes of the devices, and it was very difficult to also reproduce many of the reports from the literature, which were early reports, and the community is still learning very much on in this particular field, as the host can justify. As I really appreciate the great collaborations that I will be happy to maybe share on the next occasion on merging some of these functionalities. So definitely we are very mindful of this, and these are not only one device based approaches. These are many devices used, and there is some variability, but it's in the ranges that you can see with some of the, for example, voltage variabilities over cycles, etc. So. And personally, I could see also the differences in variability between the three-dimensional and low-dimensional perovskites, which motivated us to focus on low-dimensional systems when building these memory elements that seem much more resilient to the conditions under which these devices are measured. Very often we could not really get functional devices with three-dimensional perovskites, while two-dimensional perovskites provide the opportunity of demonstrating the effects across the larger a number of devices, which I hope helps as well in developing approaches that make these more reliable. So there is variability, but they're tolerable and the effects are consistent.
Thank you very much, Giovanna. Just to remind to the audience, next speaker will discuss about reliability. So Professor Lanza I think he will make an extended discussion about how we can produce neuromorphics with high control. Not only perovskites, I mean, even beyond perovskites. Just we have time for another question. If you are utilizing perovskite coatings,
I'm not quite sure what this refers to. Is it the coating over the perovskite, or
maybe he's referring to the passivation layers?
So the first example I tried to show involves these kind of passivation layers that are thin layers. Coatings on metallic substrates. No, we have not really been looking into these, apart from the efforts to really understand their mixed conduction, like building devices on different metal contacts, etc. But I'm not quite sure what this question refers to. Sorry if I'm not understanding well. Maybe you would like to comment? Okay. Very good. Of course, for these mechano-responsive systems, you often think about piezo responses, and this is justifiable, especially for some of the non-centrosymmetric systems, like the benzyl bromide based. And on our end, we haven't been looking into these types of responses very much over the past years, but we're very interested, especially that we are since recently working actively on metal-free all organic systems that are very promising in this regard. So I'm hoping to very nice. So I'm hoping to understand better some of the recent developments. I'll be happy to stay in touch and to learn more from your efforts on lead-free piezo nanogenerators. Thank you for sharing and dropping this message.
I guess in this kind of application, you have to develop the material on electrodes, maybe.
Yes.
That's why the applicant is asking about.
It's
If we
true.
can tell-
Sometimes, yeah. Sometimes it's just not clear what the coating refers to. You were right, Kostas. It could be also related to a passivation layer, or. And I will be happy to receive to look into your papers and stay in touch. Thank you so much.
Okay.
I guess
so-
there are different objectives of this, I guess, webinar, but one of them is also to connect the community and learn something new. So this is what's maybe to share different a variety of different approaches and ideas, so that that hopefully this serves the community to an extent.
Okay, so is there any other question from the audience? Unless I think we are on time. So now we have a lunch break for 1 hour. And we can continue after 1 hour with Professor Lanza. One comment about electrophoretic deposition. I think you can directly contact Professor Milic afterwards, and you can continue the discussion. So thank you very much again, Professor Milic. And now we have 1 hour break, and we'll continue later. Okay? Thank you very much.
Thank you so much. Thank you.
Bye bye.
Enjoy lunch.
Thank you.